This segment is about multiplication, and we're going to present an 8-bit 2D pipelined multiplier. I tried to do a 32-bit, but my simulation resources aren't quite up to the task, so we have an 8-bit. The 2D pipeline multiplier, you really have to think about it in 3 dimensions. So the presentation of it really takes a bit of hand waving and a little body English. So we're going to do the details a little bit differently than we've done them before. The details. This is the standard view of an 8x8 multiply, and it's oriented towards the addition, and it adds up the digits to be multiplied in columns. We're going to rearrange this a bit. We're going to squash it down so it's a square array, and 2 things result from this. The first is that all of the input digits are in rows and columns in this array. All the A0s are in this column, all the A1s are in this column, all the B0s are in this row, and all the B1s are in this row. So now the digits of the input variables are lined up within the array, and the partial products to be added are now diagonal in the array. So we're going to take advantage of this structure to make a 2D multiplier. And the first step of this is to make pipelines for each digit of each input. So the B's digits are going to pipeline this way, and the A digits are going to pipeline this way. This is the flow specification, and you'll notice that at the end of each pipeline, A pipeline and B pipeline, we sync them. So the end of each pipeline is sunk here, and the end of each pipeline is sunk here. We're going to do this in stages, and this is a simulation that simulates this first stage of pipelining the individual digits. Now the next stage is to put in the partial products. And as the B's propagate this way and the A digits propagate this way, they intersect, and at each intersection we'll get a partial product. Right? So this is A0, B0, this is A7, B7. When we create this array of partial products with a single array tile. So the tile is a component with internal links and half oscillations on its boundary. So this is an input half oscillation, and this is an output half oscillation for the horizontal B pipeline, and this is an input half oscillation and an output half oscillation for the vertical A pipeline. And this is the output half oscillation for the partial product. So we just tile these in here. Each one of these is a tile, and we tile 64 of these into the array, and we have this much of the array, right? So we have the array generating all the partial products. This is the flow spec, and you'll notice that each partial product now we're syncing, and then we have a simulation that will take us to this stage, right? So this simulation does all the partial products. The next stage of this development is to understand how the flow works through the array. Now, the inputs are going to be 2D pipelined inputs, so they're going to come in as slanted wavefronts, right? This is the B input and this is the A input. So the wavefronts are going to flow like this into the array, but they're going to be slanted, right? So this is a data wavefront, null, data null, data null, data null, data null, data null. And this is bit 0, 1, 2, 3, 4, 5, 6. So bit 0 comes first, bit 1 comes later, bit 2 comes later, bit 3 comes later, and so forth. The same for B, bit 0, bit 1, bit 2 later, bit 3 later. And as these digits of each set of inputs are presented to the array, they start pipelining through the array. And as they pipeline through the array and they intersect and they create partial products, the partial products are going to be created along these green diagonals simultaneously. Okay, so all of these partial products will be created simultaneously, all of these partial products will be created simultaneously, and so forth. And they will succeed each other, right? So this will be the first set of partial products produced. A little bit later, this set of partial products will be produced. A little bit later, this set will be produced. So there are waves of partial products flowing through the array, and they're not wave fronts. This doesn't flow to this and this to this. They're just you get this, and then you get this, and then you get this, and then you get this. And then the null wavefront will come through, and the next data wavefront will come in, and we can have successive data wavefronts flowing through this array simultaneously, one behind each other. So these diagonals now correspond to the adder columns in the array, right? So when we squeeze the array down, the adder columns got diagonalized, and the incidence of simultaneous partial products correspond to the partial products that we want to add together to get a product output. Okay, so now all of these happen simultaneously, 40, 33, 12. And by the way, we have a linear numbering here, 1 to 63 of the array, because iVerilog doesn't do two-dimensional arrays, and we have to do our own two-dimensional addressing. So we have a single-dimension array representing our two-dimensional array. So that's why the numbers are this way. So anyway, so now partial product 48, 41, 43, 27 are all available simultaneously to be added. So what we don't want to do is take an adder that adds these, then it adds this, then it adds this, then it adds this. We don't want a progressive adder. We want an adder that can take all of these at once and start adding them. So we're going to use trees. We're going to have a tree adder growing out of the plane of the partial products. So we'll add 40 and 33, 26, 19, 12, and 5 simultaneously, and then we'll add the sum of those and then the sum of those. So we'll have an adder tree growing out of each of these green lines. Now the carries will propagate from tree to tree. And now if you remember, the partial products are delayed, right? This partial product happens, then this partial product happens, from the pipelining of the two inputs. So when this goes up into the adder generates its carry at the same time that these partial products are ready to go into the adder. So these partial products and these carries go into the first level of this adder at the same time. So everything flows just in time as the inputs are flowing through and intersecting, creating partial products that are flowing up through the adders, with the carries flowing from adder to adder. Everything flows just in time, and there's nothing in here that slows the flow down. Nothing is waiting in this array. So now let's look at a detail of the adders. So these are the adders, the successive adder trees for each bit. This is product bit 0, product bit 1, product bit 2, product bit 3, and so forth. And this is the adder tree, the growing out of these partial products, which happen simultaneously, these which happen simultaneously. And these are the product bits coming out of the top of the adder tree, the top of each adder tree. Now the carries go from the first level of this tree to the first level of this tree. And if you remember, this tree is just a little bit behind. The input datas are flowing, and these partial products are being created. These partial products happen first, these partial products happen next. So as this is doing its add and generating its carry, the partial products are being presented here. So the partial products and the carries are presented at the same time to the adders. And you'll notice that the first level adders of each tree generate carries to the first level adders of successive trees, and the second level generates carries to the second level, and the third level generates carries to the third level. So as these trees are flowing up, the carries are flowing through the tree. So I call this an adder forest because it's a bunch of trees and they're connected by carries, similar to the trees in the jungle connected by vines. So those are the first 7 bits of the product, and these are the last 8 bits of the product. Okay, so here this is in the diagonal, and it's the biggest adder tree, and then they start getting smaller as we go down to the left corner on bit 15. But it's doing the same thing, right? Level 1 carries to level 1, carries to level 1, level 2 carries to level 2. And as the carries flow and the partial products flow and the product bits flow out of the top of each tree, we get our multiplier, we get our product. So that was an unsigned multiplier. And for the signed multiplier, we have the same scheme. We have a forest of trees with carries flowing from tree to tree, and we use the Bow-Woolley negative weighting strategy to do the 2's complement signed multiply. Okay, so the first 6 bits of the signed multiply is identical to the unsigned multiply, and then we start getting negative weightings on the 7th bit. So red is a half add with 1 input that is negated. And this is the last half of the signed multiply, and these are the negative weighted inputs to the adder tree. When we finally get down to the last bit, and we get bit 50. So let's have a look at the code first. This is the circuit under test. This is the code that does the pipelining of the A and B through the array. This is adding in the partial products, and this is in the same sequence that we did the presentation. And these are the adder trees, right? This is the tree for bit 0, the tree for bit 1, bit 2, bit 3, bit 4, bit 5, bit 6. And you can see they get a little bigger as we go up towards the diagonal. And they're all built out of full adds and half adds to generate the carries. So we get bit 7, then we go through to bit 15, which is a small tree again. So let's look at the signals now. So we have 2 sets of signals. The first is the standard library. And you can see that it takes about 52.8 picoseconds. We subtract the 2 picoseconds for the initialization, and it's about 51 picoseconds to do the test bench, which is 99 numbers to multiply, 99 vectors. So now let's look at the output. And we'll expand this. And we can see these are the products, right? This is the first product, the second product, the third product, and they're coming out skewed. And this is the last product. Okay, so those are the products coming out. So let's look at the inputs going in. So this is the completenesses for the inputs going in, and you can see that the A input is skewed. It's not what we want. This is what we want. And the B input is skewed. The product output is skewed, and they're all flowing at the same throughput rate. And the throughput rate here is 99 vectors in about 50 nanoseconds, so it's about 2 gigahertz with the standard library. Okay, so we'll shrink this back down, and we'll look at the library with the multiplier with the unity library, and we'll see that that takes about 3.2 picoseconds to complete all 99 vectors. Now it looks like this may not have worked, right? This just didn't take long enough. But if we expand it out, we see that it's all there. And the standard library passed the test bench, which was checking for the validity of all the outputs, and in the Unity library also passed the test bench, right? So it passed the test bench, and all the signals are in here, but this whole thing happened in about 1.2 nanoseconds as opposed to 50 nanoseconds. So that's an indication that the multiplier really is logically determined and really insensitive to the delays. Okay, so this is the product output, and these are the inputs. All right, this is the A input and the B input. And they're not quite as slanted as they were before because the time's compressed. But anyway, they're all there.